To start this lecture, we're going to be working on the concept of thermodynamics. You may remember that in 1211 you covered a bit about thermodynamics when you talked about enthalpy. We're going to add a few more terms here, although we'll keep using enthalpy as well. So if you don't remember that, it is a good thing to review, although we'll also do some work with it when we get back to it as well in this section. So, in general, the reason we care about thermodynamics is because it's going to predict whether a process is going to occur or not. So what we mean by this is processes that will occur as we have them set up are something we call spontaneous. So if a reaction is spontaneous, that means if I just let it there in its current conditions, it will happen. If a reaction is instead non-spontaneous, I'm going to have to put energy into the system to make the reaction go that way. As a side note, it's important to remember that spontaneity doesn't relate to whether the reaction is fast or slow. That was kinetics. So for example, if you have a diamond, if you give it infinite time, it will eventually turn into graphite. Having said that, no one is ever stressed out, or maybe someone is, but most people don't think about it, and if you have thought about it and you know some chemistry behind it, you know your diamond ring, if you get one, is not going to turn into graphite within your lifetime, within your kid's lifetime, or within your grandkid's lifetime. It's not going to happen. It's not going to have any significant move towards that. So technically it is true. Diamond spontaneously turns into graphite. But it, under normal conditions, aka 25 degrees Celsius, 1 atmosphere of pressure, does not happen at a very significant rate at all, so it doesn't cause us concern. Other conditions you might worry about, such as if this diamond needed to exist for 1 million years, what would happen to it? That's a different setup, and then you might be concerned about it. But for the time spans we're worried about, it's not a big deal. Having said that, some other processes, it will be a big deal. But overall what's important is it will happen eventually. Other processes called non-spontaneous won't happen. So graphite, even if I leave it out on the table for 1 million years, won't turn into diamond if it is at 1 atmosphere of pressure and 25 degrees Celsius. There may be some other conditions, such as increased pressure, where you could turn it into diamond, but just sitting graphite out, even if I'm giving it infinite time, unless I do something else different, it will not be spontaneously turning into diamond. It will stay graphite. There we go. So, to talk about this thermodynamics, we need two values. Enthalpy we covered in 1211. We'll review it a bit when we get to combining these. But the other one we haven't talked about yet. It's something called entropy. Now, I will say straight up, we're not going to give the most clear definition of entropy. Well, not that it's unclear intentionally. It's that it is a fairly complicated concept and that we do our best to describe it here. But as you further study inside of science, I think you'll get a better picture, especially when you have a slightly stronger mathematical construction to apply to it and to think through some of these ideas. But we'll do our best here. But do understand that if this is a topic that is bothering you, I do think it is worth putting more time into reading and learning about it. It's just that it is a reasonably complex topic. And so I think it has some value in there if it's bothering you. So what we're going to do in chemistry is we're going to say entropy is a thermodynamic function. So we use it with our state functions and all those ideas that we talked about in 1211. That what it does is it increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. Now that sentence doesn't sound like it means much at all. So a way to break that down is actually with this example here. So you'll see here we have sodium chloride, and it can be in a solid form, or it can be dissolved in water, and it can be separated into its ions. In the solid form, there aren't many configurations of it that are successful. It has to be basically all the atoms are right next to each other. They can move a tiny bit, but there's not a lot of give. They can't change their location much and still be the same thing. But with sodium chloride and water, once it's dissolved, it's able to spread out really well. And then it's able to make all kinds of different configurations, which means it can move around a lot, and that means you're going to have a greater entropy when you're working with sodium chloride in the dissolved form, because there's a lot more ways it can take that form. Note, we will be going through a bunch of different examples of things that increase and decrease entropy if you're not sure yet, but the general idea is we're counting how many different ways we can arrange these systems where they are still the same thing and arranged in the same way. So, another example is when water evaporates. So liquid water does have some entropy because it's able to move around some, but it's still constrained because the water molecules attract each other, and so they're going to stay in about the same place. Your liquid water doesn't suddenly spontaneously form rain droplets and rise up into the air, right? If it wants to rise in the air, it's instead going to turn into a gas. And once it becomes a gaseous molecule, it's able to move around a lot more. There are a lot more arrangements because it's not restricted by nearly as many molecules. So it's able to take a lot more different configurations, so it increases in entropy as you go from liquid to gas. So those are two big ideas with it. Now we're going to go into some particulars, the rules we need to know to be able to work with this idea. Stick with me, and I promise we will get through this and we will show you how to make this usable. So first, a review from 1211. Your first law of thermodynamics is that energy cannot be created or destroyed. That means if you have a system and its surroundings, remember, the system is the thing we're studying, like we talked at 1211. The surroundings is everything else around it. So for example, you might be studying what's happening inside a beaker. That's your system. The surroundings is literally the rest of the universe, although practically speaking, you're mostly looking at what's happening right around the beaker. But technically speaking, the surroundings is literally everything else, and the system is your little beaker where your reaction's happening. So the total energy of the universe cannot change, but you can transfer it from one form to another or from one place to another. Now our second law of thermodynamics, which is the new one we've got to introduce here, we didn't talk about entropy in 1211. It says that the total entropy change of the universe must be positive for a process to be spontaneous, which is a way of saying if something will occur naturally without having to put energy into it, it just occurs where it's sitting there, it will increase in entropy either the system itself or the surroundings around it. You may remember in 1211 we used the word reversible process a time or two. All that means is if you've got something that just goes back and forth without significant changes, in that case delta S universe equals 0, because it's at two states and they don't make any changes for the most part. On the other hand, because it's moving infinitesimally small amounts of whatever change it's making. On the other hand, if you have an irreversible process, something that might be spontaneous, delta S universe is going to have to increase in this case. So, if the entropy of the system decreases, then the entropy of the surroundings have to increase a larger amount, or else it wouldn't have been spontaneous. You wouldn't have delta S universe greater than 0. So, when delta S is negative, delta S surroundings has to be positive, and it has to be more positive than delta S system was negative. So the important part here is we can't cheat entropy. This is where people talk about things like the concern about the heat death of the universe. The idea being is that we have to have constantly increasing entropy for the entire universe. We can't decrease it for the universe. We can decrease it in one little region where we make one little region more ordered, more structured so that it doesn't have as many configurations, but that had to cause other parts of the universe to increase in entropy to make that occur. So what we're going to cover here is an idea of how to think about the idea of entropy. And I'll admit that at very first I think it's a little hard, but I think when we look at a couple of examples, it'll feel a little better. So we're going to use two terms. We're going to say macrostate and microstate. So a macrostate is going to be something like, in this example, we have two flasks. We've got 4 molecules. So the macrostate is having any 4 molecules in flask 1 on the left. Let's label these. So we have 4 molecules in 1. A macrostate, another one would be 4 in flask 2. The microstate worries about which of these molecules is in each flask. Now in this case it might look kind of silly, they're the same thing. So the microstate version of state A, there's only one answer. Molecule 1, 2, 3, and 4 all have to be in flask 1. Because if any of the flasks were in flask 2, it would no longer be the same macrostate. So in this case, we don't have to worry, microstates are the same thing, they look like it's just the same name. Let's look at a second example, and we can use this to talk about entropy. So let's say our macrostate is 2 in flask 1. I'll call it flask A. That way we don't have to worry about numbers looking the same. And then 2 in flask B. Now for that macrostate, you can go through and figure out there are 6 different ways to configure that on the microstate version. So for example, if you have molecule 1 and 2 in flask A, then molecule 3 and 4 can't be there because you can only have 2, so they've got to be in flask B. On the other hand, let's say we took 2 and 3. Well, then 1 and 4 would be in flask B. You can figure out every possible configuration. We're not worried about the order that they are in the flask, or how many molecules are in each flask and which flask are they in. You end up getting 6 different versions of the macrostate 2 in A, 2 in B. So, macrostate for state C can have more configurations than the first 2 states we looked at. That's what this slide goes with, I just remembered. So we'll talk about this one. So, if I were to compare state A, B, and C, I would say states A and B have the same amount of entropy. They only have one possible arrangement. State C, on the other hand, has 6 possible arrangements. So it has greater entropy than states A and B that can only be arranged one way. So this is working with a very small number of molecules so that it's something you can see. I will say up front, when we're working with actual molecules inside of our class, you're working with moles of molecules. You will not try to count microstates with your mole of molecules. But you can use this same concept of, oh, if there are more ways to arrange this in this particular configuration, then it's got to have higher entropy. So, yeah. What I will ask about for questions is I'll ask a simple case like, oh, you've got 4 molecules or 6 molecules. This is a way to work with manageable numbers. I will point out that you probably realize you're not going to have a flask with 4 molecules in it, really, because that's so few, it's insane. Like, you couldn't work with this in reality under most conditions. I say most. If you want to go work with ultra-high vacuum chemists, we can get very few molecules, maybe not 4, but we can really take a lot of air out of things and really shrink how many molecules are in something. But under most conditions, you're not going to deal with this. Also, there are people that use computers to make calculations like this about microstates. Once you get a whole bunch of them, computers can work with this, but we're not going to work with that with this class, and you probably won't work with that problem in undergrad. But if you go to graduate school, we deal with that a little bit. So now we've talked about how to measure entropy. So, in chemistry, we do a lot of chemical reactions where we change things. So we also know how to talk about changes in entropy. So we're going to use this term, delta S. And that's going to be S final minus S initial. So if you can get numeric measurements for the final entropy and the initial entropy and you subtract them, that's the change. So entropy change is going to be favorable when the result is a more random system. So a more random system, remember, is going to make higher entropies. So if S final is bigger than S initial, that means that there were more microstates that were possible for that macrostate for S final. So it had more possible arrangements. In that case, delta S is going to be positive, and that's going to be a favorable thing. So reactions that when delta S is positive are more likely to be spontaneous. Note, I said more likely, not guaranteed, because we're going to have another term later that helps us calculate both the delta S and the delta H stuff you've already learned. So both the entropy and the enthalpy both matter. We got to go through all the entropy stuff first, though. So since we're talking about delta S, what kind of changes can come up? I lost my marker, and I know it's moving around the screen probably for you guys. There it is. So we've got 4 total changes we're going to work with, and we're going to look at examples of these throughout the next few slides. So 1, reactions whose products are in a more random state. The main one that comes up here is that solids are really ordered in their structures. They can't take very many arrangements, whereas liquids are going to be less ordered. And then follow up even further, gases are even less ordered. So if you've got a phase change, you can use that to figure out, oh, I had solid to liquid, that's an increase in entropy. Oh, I had gas to liquid, that's a decrease in entropy. So number 1, look at the state. Number 2, reactions that have larger numbers of product molecules than reactant molecules have higher entropy. So if you start with a reaction that had 1 molecule of A in the gas state, and it turned into 2 molecules of B in the gas state, this is going to be increasing entropy because you have more molecules on the right than the left. Or it might even be written as like A gas turns into B gas plus C gas. So it doesn't have to be the same molecule. This turned from 1 to 2 though. 3 is increases in temperature, increase entropy. We've got more energy. They're able to move around more. There's some different reasons that it's going to be higher in entropy if the temperature is larger. And then finally, when solids break apart into their ions, when they dissolve, that increases entropy. So like if you have an NaCl solid and you put it into a beaker of water, so we're going to add that in there, what's going to happen inside is you're going to get Na pluses and Cl minuses. So now you've separated that, which means you now have more molecules, but also each of those the reason why we say more is because each of those ions can now move around and be surrounded by water, and it's got more ability to move around. It's less restricted in what it can do, so it has more possible states. So we put our salt in our water, now it's turned into Na plus and Cl minus, it's at a higher entropy. So this is just a graphical representation of that. You'll notice this covers both temperature and phase change. So our entropy starts technically at 0, so if you get a solid that is perfectly crystalline at exactly 0 degrees, you have literally 0 entropy. Note, we have never gotten a solid to exactly 0 degrees Kelvin, so this is theoretical. we've gotten it really, really close to 0, but not quite there yet. So this currently is still one of those things that we theorize with and use as a useful tool, but we've never reached exactly 0. And we don't know if we'll ever be able to. But at least in theory, it should be at 0, and it's incredibly low for things close to 0. So as the temperature goes up, you'll notice the entropy increases. Then you get to this area right here where it melts, and that's going to change drastically how many configurations it can take. So once it's a liquid, it's now changed its entropy by a lot. It went up. Then if it evaporates into a gas, it increases even more, and now you've got higher entropy. And the gas, even in its phase, as its temperature goes up, the entropy keeps on increasing. This covers both the temperature and phase change version. So let's look at these. I'd like you to pause the video now and try to predict for all 3 of these what should happen in the process. Hopefully you've given it a try. Let's look at A. A, we have gas to liquid. So the gas is the higher entropy state because it went solid lowest, liquid in the middle, gas highest. So this is a decrease in entropy. I've really got to get better at where this thing is. So this is a decrease, which means delta S will be negative. Now B tests some terminology we used earlier in the semester. So this means that CO2 solid turns into CO2 gas because subliming is solid to gas. So remember, solid had our lowest entropy and gas had our highest. That means for B, delta S is going to be positive because it increased in entropy. Now for C, they're all gases, so we can't use that. But we have 2 molecules on this side, 3 on this side. So as you increase number of molecules, so increasing molecules leads to increasing entropy. So that means our delta S will be positive. So now we've gone over that. To be able to use this to do more calculations with, we have to have a few more terms. I know it's a lot of terms today. We'll do more problems in the next lecture. We'll do a few in just a minute. But there's just a lot of things to cover to be able to do anything with this. So we actually covered this part in 1211, but this is a refresher. Your standard state is the state of the material at a very specific set of conditions. So the standard state for a gas, something is naturally a gas, is a pure gas at exactly 1 atmosphere of pressure. A solid or liquid is a pure solid or liquid is in its most stable form at exactly 1 atmosphere of pressure and temperature of interest, which we're going to treat as 25 degrees Celsius unless for some reason your problem tells you otherwise. And that's what all your tables are going to be in. And then if you have a solution, that is the substance in a solution with a concentration of 1 molar. So it's not like 2 molar or half a molar. At a standard state condition, it is exactly 1 molar for that. And we mention this because you'll be able to look up what the values for entropy is, as well as enthalpy at these standard states. We have tables of those, and you can use that to figure stuff out. So our absolute entropy is specifically for our standard state conditions. Our entropy is an extensive physical property of matter. And so that's important to remember. That means that it's going to be a specific number that we can measure, and it depends on how much we have of our substance. So if you have more, it has more entropy. This is different than, for example, molarity. So molarity was intensive because a 1 molar solution in a swimming pool is the same concentration as a 1 molar solution in a glass. Like if you pull a glass out of your swimming pool, the molarity didn't change between the swimming pool and the glass. They're both 1 molar. But their entropy did change. It depends on how much you have. So the entropy for 1 mole of a substance at 298 Kelvin for a particular state, so solid, liquid, gas, aqueous, a particular allotrope, that's something we'll cover in a couple of slides. It's just a way of saying some solids, for example, can have multiple ways to arrange themselves. So a particular form of the substance, a particular molecular complexity. So, for example, my entropy of a carbon atom and an oxygen atom is different than a carbon monoxide where the C and O have combined. So it has to be for a particular molecular complexity and a particular degree of dissolution. That means that NaCl solid has a different entropy than NaCl that has been dissolved in water. So these are all the things we have to worry about. State, something we'll call an allotrope, and we'll look at an example in 2 slides. Molecular complexity, how are they bonded? And then degree of dissolution, are they dissolved or are they solid or somewhere in between? So we're going to finish up before we go over all those with our third law of thermodynamics. So we had our first law, energy can't be created or destroyed. Our second law, entropy for the universe has to increase always. Our third law, and note I said entropy of the universe, your system can have a decreasing entropy, but that means the surroundings have to increase. Your overall total entropy for everything in the universe always goes up, never down. So our third law is that if we have a perfect crystal at absolute zero, the absolute entropy is 0 joules per mole Kelvin. Therefore, if your substance is not a perfect crystal at absolute zero, it has an entropy, and that entropy is positive. So your delta S could be negative sometimes of what you're measuring, but S itself of any particular substance is always positive unless it's 0 degrees in a perfect crystal. And other than discussing theoretical substances, so far science chemists have never made a substance, at least as of recording of this, at 0 degrees Kelvin. So everything in the known universe currently has entropy to some amount. This is just a table. You can use this on some of your problems when they come up. This is an example of how we can look up entropies. These are the entropies for these different substances, and they've been measured. So for example, hydrogen gas right here has 130.7 joules of energy per Kelvin, so it depends on the temperature, and per mole. So 1 mole of gas has one amount of entropy. 3 moles of the same gas has 3 times as much entropy. So we worry about how much we have. And so these are the most common substances. They'll be useful, for example, on your problems on Pearson. You can also refer to this in your textbook as well. But this is just so it's in the slides in case you didn't have easy access to your textbook. So let's look at the things that increase our relative entropies. So in general, if nothing else changes about complexity of the molecule or phase or anything like that, higher molar mass means it's going to have a higher entropy. So the example here is a series of the noble gases, helium, neon, argon, krypton, xenon. We choose these because they're all the same phase, they're not bonded to anything, so they're about the same complexity. They're one atom. You'll notice the entropy increases, and that's as the molar mass gets bigger, each of those atoms is bigger than the one before it. Now, allotropes is the one that is probably the one you may not have heard of before, and I'll be the first to admit, in this class, we're not going to cover very many allotropes. Mostly we cover carbon because it's the one that matters a lot. There are some others, but this is where we're mostly going to stick to. The idea behind an allotrope is that it's different ways of having the atoms arranged. So what you'll notice is, in the diamond here, you see how these bonds right here connect. So what happens is you have atoms that exist in this sheet-like structure above it. And note, I'm not drawing all of them. They go like that, and there, and there, and there. So this is all one flat layer. I suck at drawing. Look at the drawing in the text. I'm just trying to help. But what happens is there are more lines that connect to sheets down below. So if there's another sheet below it that is connected, those atoms also bond up this way. I kind of drew a cube. I'm pretty bad at this, so I'm definitely never winning any medals. But I'm trying, I promise. So they have these here. In graphite, though, when they have these sheets, so they still have the sheets, but the way they're bonded, those sheets don't connect. So there's another sheet down here. This is one reason why we talk about pencil lead. Pencil lead is not lead, it is graphite. And so it's got these sheets, but the sheets are not connected. So right there, no connection. What's important about that is that lack of connection means there is more freedom of movement, there's less constraining on the graphite compared to the diamond. So graphite, since its layers aren't connected, has a higher entropy than diamond. So we can do this with other structures as well, that we do have other molecules that will have allotropes that they can have different ways of being arranged, but by far the most common used in your text and the main one that comes up is diamond versus graphite. If you have another one, we will also give you values you can work with. You can't just come up with the values out of nowhere. Or we'd have to give you some information so you could figure out which should be higher or lower. The higher one being the one that's less constrained. So if you read some wording and one said this one is connected a lot, and the other one said this one's connected a little bit, the one that's connected a little bit is the one that has the higher entropy. It's able to move around more, assuming all else is equal. So third, we said molecular complexity. So these are some ones, and I'm going to choose some specific examples. So first, let's compare CO to C2H4. Carbon monoxide has 2 atoms with 1 bond. C2H4 has 6 atoms, and I'm going to guess I should draw it correctly. If we look at it, it forms this molecule here, And we have a total of 1, 2, 3, 4, 5 bonds, or 6 bonds, depending if you want to count the double twice. For the purpose of molecular complexity, I'm going to count it 5. You don't have to worry about that. I'm just pointing out there's more atoms, there's more bonds. We will pick examples where it's clear. Their molar masses, though, if you look at those, are about the same. So the molar mass rule by itself wouldn't be enough. But this is higher than that one. I said this in words. That's a bit. The second one is bigger. The first one is smaller. That's because there's more molecular complexity. Now, on the other hand, so I'm going to erase this ink because I want to make a second example. Let's take 2 and 4, the C2H4 and the argon. So what you'll notice is here, this is 219.3. This is 210.8. But argon has more molar mass. So if the molar mass rule by itself was enough, that would mean that argon should have a higher entropy. But C2H4, on the other hand, has more molecular complexity. Therefore, C2H4 can end up with a slightly higher entropy, even with a lower molar mass. Now, I like showing that example, but I would like to point out, if you have to come up with a trend on your own, if I had to say here are 2 molecules, which has the higher entropy, I won't ask you for competing trends. I couldn't give you C2H4 and argon and ask you which has more entropy, because in one way, molar mass says argon, but molecular complexity says C2H4. So I like to show this example of how multiple of these can interact. But for the purpose of questions where I just ask you which has higher entropy or lower, I'm only going to look at one trend at a time. Or if there are 2 trends, they're both going to go the same way. So I won't ask for competing trends because that's not fair. You don't have enough information to do that. So then we said dissolved solids have larger entropies. So KClO3, if we dissolve it in water, turns into K plus and ClO3 minus. Since this is dissolved in water, it's able to spread out a lot more. It's able to take on a lot more configurations. It has a higher entropy than the solid version of the substance. This one's one of the more straightforward ones. Solids versus their aqueous components. The aqueous components are going to have a higher entropy. So numerically, the way we can work with this is the delta S for our reaction is we take all of the products and the number of moles, and we add all that together. Because remember, this symbol here just means sum. And I'm going to do an example on the next page if you don't get what I'm talking about. And then from that, we will subtract the sum of all the entropies of the reactants, which we have to multiply by n, how many moles there are. So that's because it's an extensive property. It matters how many moles were there. 4 moles of something has more entropy than 2 moles of the same thing. So it's also important to remember, in 1211, we said that the standard enthalpy of formation, delta HF, of an element is, I'm not trying to cross that out, I'm trying to underline it. Hey, got a break from me talking to you. Of an element is 0 kilojoules per mole. That's true. Delta S, though, is positive, not 0. So if you ask for the entropy of any one thing, unless it's a 0 degree crystal, it's going to be positive. So what does this look like? Let's take an example. We're going to look at this reaction here. It's solved in your textbook as well. 4NH3 plus 5O2 reacts to form 4NO plus 6H2O. So what we do is we take the delta S of our reaction. It's going to be products minus reactants. So first, our first product is NO, and it's got a value of 210.8 joules per mole Kelvin. So we'll have 4 times 210.8 joules per mole Kelvin. I want to point out the units are especially important in these problems because entropy is going to be in joules, whereas when we get the enthalpy from last semester, it was in kilojoules. So we do have to do some conversions. So make sure you pay attention. The units aren't just an add-on at the end. Our second one is water. It's the second product. There's 6 water molecules, and each has an entropy as 188.8 joules per mole Kelvin. Note, I got that literally right here from this table. It's not something I memorized. So we're going to add all those together. We're then going to subtract the entropy of the reactants. So first we have ammonia, 4 times 192.8 joules per mole Kelvin, plus 5 oxygens. So in 1211, with the enthalpy, we would have just said, oh, it's oxygen, 0. But for entropy, it's going to have a value of 205.2 joules per mole Kelvin. So now, when we get those values, we're going to get the products, when we total all of that up, is 1,976 joules per mole Kelvin. Whereas now we're going to subtract the reactants, or for the reactants I get 1,797.2 joules per mole Kelvin. So if we combine all those, we will get an entropy change of 178.8 joules per mole Kelvin. So when this reaction occurs, entropy increases by this amount. I didn't mean to cover up the top of the J. They're supposed to be. There we go. So this is how we do this. These problems don't change a whole lot. They're going to be, find this entropy. That's what you do. So how do we quantify the entropy change in the surroundings then? I just showed you how to, I've been talking so far about systems. So from 1211, we said Q surroundings equals negative Q systems. So this is when we're dealing with heat. So heat changes. Whatever happens to surroundings, the opposite happens to the systems. So the entropy change in the surroundings is also inversely proportional to the temperature. So we are going to work with constant pressure systems. So what does that mean? For example, you have a flask. It's sitting here. You add a reactant. And it does something. Let's say it's like a solid that dissolves. So that has a change that occurs with it. This is going, the reason we're going to say it's at constant pressure is because it's sitting there in the room. The pressure is going to stay at 1 atmosphere of whatever the pressure of your room is. It doesn't suddenly increase to 2 or 5 atmospheres. As long as we have an open container out to the atmosphere, it's going to stay at constant pressure. Any small changes will adjust. It'll be a practically no change. We're going to treat it like zero change when the number of molecules increases or decreases, because it is insignificant compared to how many molecules are literally in the room of air. We're not going to make enough air to suddenly have a pressure of 2 atmospheres in a room that was at 1. Or if you did a reaction big enough that it would be dangerous or cause some issues. You're not doing anything nearly that big. On the other hand, imagine we took a flask and we add reactants, and then we seal the flask. Seal, now, no longer constant pressure, because the gases that it creates can't get out. So anything we do to change that is going to cause changes, because now, if there's more molecules, there's no space for them to take. Having said that, as a reminder, you don't tend to seal reactions, at least in flasks, that do this, because if you increase a bunch of pressure, you'll literally shatter it or pop the seal off. There are containers we build for this, and some reactions is okay because they don't cause large pressure changes. But for us, we're mostly going to work with the beaker sitting on the countertop where the pressure is constant. It is only true, this statement down here is only true for constant pressure. The reason we say this is in physics, you will probably cover non-constant pressure systems. Or, if you stick with us in chemistry, in thermodynamics, you will definitely cover non-constant pressure systems. We are going to stick to constant pressure, where there's some rules we can use. And that is, the entropy change of our surroundings is equal to the negative Q system, so whatever happened to the system, if we negate that, that'll give us Q surroundings divided by the temperature. Note that Q system, we learned in 1211, was also equal to enthalpy of our system. And we keep the negative. So, delta S, if we want to know the change in entropy of our surroundings, it's going to be negative delta H system over T. And so this is something we can look up or measure. Well, we can look up. We'd have to do some other things to measure. So we can look up and figure out how much did the enthalpy change for the system. Whatever happened to that, the opposite has to happen to the surroundings. We have one final concept before I finish here. I'm going to do one more thing. I'm going to cover the idea of Gibbs free energy. And we're going to introduce this, and we'll do a lot more detail in the next class. So, Gibbs free energy is the most used. Everything I've said so far about entropy is important. In terms of practically how you're going to use entropy to learn something, though, is to combine it with enthalpy. So Gibbs free energy is where we combine the enthalpy and the entropy together. Note, I give the technical definition here. It's the maximum amount of work energy that can be released to the surroundings by a system for a constant temperature and pressure. You will mostly stick to using this chemical equation to figure things out. So delta G, your free energy, I'm less worried about the technical definition and more about the fact that it is equal to the change in enthalpy of your system minus T delta S, temperature times the change in S. The reason why we worry about this is delta G is what's going to determine what reactions are spontaneous or not. This is helpful. I would like to be able to predict if I mix two things together, is the reaction I want going to happen, or is it just going to sit there and not do anything? So I want to know, is my reaction spontaneous or not? This is the practical reason we said all that stuff about entropy and all that stuff about enthalpy in 1211. There's other things they tell us, but the main use we have is, does my reaction happen or not? That's what we want to know. So, how does it determine spontaneity? A process will be spontaneous when delta G is negative. So, when is delta G going to be negative? That will happen if I pressed a button. There we go. If delta H is negative and delta S is positive, it will always be negative. The idea is you plug a negative in here, and then you plug a positive in here, but you're subtracting that positive number. So you get a negative and another negative. You combine those. Remember, you're combining these, you're not multiplying them. Two negatives combined together make a bigger negative. So if delta H is negative and delta S is positive, you have a spontaneous system always. On the other hand, if it's the other way, so this was spontaneous always. But if this is positive and this is negative, since you're doing a negative of a negative, that means you're adding two positives together. This will be never spontaneous. So these are the easiest cases. So if the signs are opposite, it's always going to be either always or never. You don't have any additional work to do. On the other hand, if they're both negative, then it's only going to be spontaneous at low temperatures and non-spontaneous at high temperatures. Note, on the next slide, I'm going to show you how to calculate what low and high means has a technical meaning in these problems. So I'm going to clear out this ink. So the idea behind this is if this is negative and this is negative, when the temperature is low, delta H dominates. So low temperature means delta H dominates. It's the most important term. That's because once you get to a high temperature, so at high T, delta S dominates. What do I mean by that? Well, since we're multiplying times temperature, and temperature is always a positive number, as T gets bigger, T times delta S also gets bigger. So the sign for that matters the most. So at really, really big values, so imagine we had something like delta H, imagine delta H is 10 kilojoules per mole, and delta S is 0.10 kilojoules per mole Kelvin. So if we start at really low temperatures, imagine we start at literally 1 degree Kelvin. Well, we're going to go with negative values for these. So negative 10 kilojoules per mole and negative 0.1. I'm trying to make it negative there. So at literally 1 Kelvin, you have negative 10, and then because of this negative here, negative times a negative, you'd have negative 10 plus 0.1. That'd be negative 9.9. So this would be spontaneous. However, as your temperature goes up, this term here gets bigger, but this stays the same. So let's imagine we had a really high, let's do a really high temperature to make it easy. Let's do 1,000 Kelvin. So you have negative 10 plus, well, we'll start it with a minus, and then you have 1,000 times negative 0.1. Well, 1,000 times negative 0.1 is going to be equal to negative 100, and then a negative times a negative makes a positive. So you have negative 10 plus 100, which gives you 90. So now you're non-spontaneous. So in the case where they're both negative, that means that the sign of delta H is going to matter at the low temperatures. So since they're both negative, that means at low temperatures, delta H wins, which if it wins, that means it determines the sign. So at low temperatures, delta H, if it's negative, means we're going to have a spontaneous reaction. Now, at the high temperature case, S wins. So if S is negative, that means that overall value, because we're subtracting it, becomes positive. And that means it'll be non-spontaneous. The opposite happens in the latter case, where you have both are positive. Then, at low temperatures, since delta H wins at low temperatures, it's going to be positive, which means non-spontaneous. Once the temperature gets really high, the entropy term wins. And since we're subtracting it, we subtract a positive, it becomes negative and becomes spontaneous. If you memorize this table, it will help you a lot with a bunch of questions. A lot of this chapter is going to be, and a lot of your questions are going to be, is this spontaneous or not? Figure out delta G. And if you can figure out these signs, you can figure out how much work you have to do. So I'm going to do one last problem, and then we will be done. So this is to show you how to calculate delta G's. So we're going to start with A. We're going to calculate delta G and figure out whether it's spontaneous or not. So delta G equals delta H minus T delta S. In this problem, it's given to us. So I can literally plug those values in. Delta G equals 95.7 kilojoules minus, our temperature is 25 degrees Celsius, which will give us 298.15 Kelvin. So we have 298.15 Kelvin. And then we have the entropy change. This is in joules, so I convert it to kilojoules. And that'll be 0.1422 kilojoules per Kelvin. So then I can calculate that. If I add that all together, I'm going to get 138.1 kilojoules. Note, it'll be positive. I'm sorry, that is not 130. Let me fix that on my calculator. So we have 298.15 times 0.1422. I subtracted it. That's why I was getting the wrong answer. 0.1422. And then we do 95.7 minus that number. There we go. That's a much more reasonable answer. Our delta G is equal to 53.3 kilojoules. This is positive. That means this is not spontaneous. So that gives us our answer to A. Now what we have to figure out, though, in question B, is what temperature will it be spontaneous? So it's a big highlight. If we want to find temperature of spontaneity, I might have spelled that wrong. We need to find when delta G equals 0. Note, if delta G can't equal 0, then it is either always or never spontaneous. So the times that happens is you'll get an answer like you would need it to be negative 600 Kelvin. You can't have negative 600 Kelvin. So therefore, delta G can't be 0 in those cases, which means it's either always spontaneous or never spontaneous. In this case, though, since delta H and delta S have the same sign, we said that if they had the same sign, then it would sometimes be spontaneous and sometimes not. Therefore, we know we can find a specific temperature where it changes. When delta G equals 0, so when delta G equals 0 is the line that divides low and high temperature. So it is problem specific whether we call a temperature low or high, and that's always going to be relative to when is delta G equal to 0. Everything below that is low, everything above that is high. So I'm going to erase this ink so we've got more room to work. So we need to find out when is delta G going to be equal to 0. Remember, delta G is delta H minus T delta S. So now, delta G is 0. Delta H is still 95.7 kilojoules. What changes is we no longer know the temperature. It's not 25 degrees anymore. And then delta S is 0.1422 kilojoules per Kelvin. So I move this to the other side. I get negative 95.7 kilojoules equals negative T times 0.1422 kilojoules per Kelvin. I can multiply both sides by -1. That makes these positive. Then I'm going to divide both sides by 0.1422 kilojoules per Kelvin. 0.1422 kilojoules per Kelvin. That'll make these kilojoules cancel and these whole things cancel. When I divide 95.7 divided by 0.1422. I'm going to get that my temperature at 673 Kelvin is what temperature I have is, this is the temperature for delta G equal to 0. So now the problem asked us, we're almost done, and this is one of those things where you're close to done, but it says it wants to know at what temperatures is it spontaneous. So we have to figure out, it's not at exactly 673. It's either going to be more than or less than. So we have to figure out based on our sign of delta H and delta S. And in case you can't remember, we can actually go back to the last slide. If they're both positive, it's spontaneous at high temperatures and non-spontaneous at low. This is an example of why you want to memorize this or know how to reason through it. That means if both positive means it's at high temperatures, that means it will be spontaneous when temperature is greater than 673 Kelvin. And note, you will have to know this. There's a good chance that a test question very reasonable, you would have one multiple choice answer be greater than and one greater choice be less than. So you need to know which direction it would go in. That is an important part. So since they are both positive, it will be spontaneous at higher temperatures. And so we plug all that in and we get there. So that was the last thing I wanted to cover. We will do a lot more with delta G on Thursday, and we'll do some practice at the start of that as well. So hopefully this makes some sense and can help you out some. I hope you're doing all right, and I will, I guess, not see you on Thursday, but I will make videos on Thursday that you watch and listen to me, which is kind of like seeing me. Or if someone's watching this in the future, this may not be a Tuesday or Thursday, but for this current recording for my live class, it is there.